Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're going to continue with our series on writing a ray tracer from scratch in C++ using the SDL2 library. And in particular what we're going to look at today is actually beginning to do some ray tracing. So if you remember the previous episode and the one before, we've really just been building up some of the theory about how ray tracing works, and we've been establishing our code base that we're going to use to build on to actually create our ray tracer. So today, in this episode, it's going to be the first one where we actually do some very simple ray tracing, and we're going to create a very simple image of a sphere, as you can see here. Okay, pretty simple, nothing complicated really in terms of ray tracing, but really gives us a good solid base from which we're going to go on to build more complicated and more interesting things. So I want to start the video, as with all of the episodes in this series, we're going to take a quick look at the theory of how we actually do this. So we are, as we discussed in the last episode, going to be casting rays into our scene, and in order to actually render an object like a sphere, we need to test for intersections between those rays and the sphere itself, which of course we define mathematically. So at the start of this video, we're going to take a look at that and see how we do that, and then after that we're going to go on and I'm going to go through writing the code to actually implement this to make it work to produce the image that we've just seen. Okay, so anyway, really hope that will be of interest. Just before we begin, I want to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Right, without much further ado, let's jump to it and let's have a look at the theory of how we can actually test for ray-sphere intersections and how we can actually therefore begin to implement ray tracing. Okay? In the last video, we were looking at the problem of camera geometry, and I demonstrated how ray tracing works by casting rays out from a point through pixels on a virtual screen and into the scene. We ended up with the illustration shown here, where the cast rays are shown in blue, with one ray for each of the pixels shown in yellow. In this episode, I want to focus on what happens when one of these rays that we have cast into the scene encounters an object. The object could be anything, but to keep things simple, we're going to start by looking at a sphere. The first thing that we need to do is understand how to define a sphere mathematically. That's actually quite easy, and to illustrate how this works, we will consider a sphere of unit radius centered at the origin of our coordinate system. A sphere in mathematical terms is an infinitely thin shell or surface, the points of which are all an equal distance from some point in space, in this case the origin. Incidentally, in mathematical terms a solid sphere would be called a ball, but that doesn't need to concern us right now. So, if we consider all of the points that are exactly 1 unit distance from the origin, something like this, we can consider each point as a vector of unit length from the origin. The end of the vector then represents a point in space that lies on the surface of our sphere. As we include more and more points, you can see how they begin to describe a spherical surface. In reality, there are of course an infinite number of points that lie on the surface of a sphere, so if we consider them all together, we get a spherical surface as shown here. So, we can see that a spherical surface consists of all the points that are the same distance from the origin. We know that in Cartesian coordinates, the distance of a point from the origin is given by the square root of x squared plus y squared plus z squared. Since we know that all the points are the same distance from the origin, we can write this as r squared, or the distance from the origin, is equal to x squared plus y squared plus z squared. And this is the equation for a spherical surface. In vector form, this becomes the square of the norm of x, where x is the vector of points, is equal to r squared, where, as before, r is the distance of the points from the origin, or the centre of the sphere. We can define one of the rays that we are casting into the scene as a line. Of course, in mathematical terms, we can define a line between 2 points using the starting point, shown here by the blue ball on the right, and a direction, defined here by the blue arrow. All of the points that lie on this line are then given by the equation x is equal to p1 plus tv, where p1 is the start point of the line and v is a unit vector that defines the direction. T is a scalar quantity that defines some position along the line. If we vary the value of t, we get different points that lie along this line. If we extend this line out so that it passes through the sphere, like so, we can see that the points where the line passes through the sphere will be the points that lie both on the spherical surface and the line. So we can find the locations of the points of intersection of the line and the sphere by making the two equations equal to each other. This will give us the equation that we have here, where p1x plus tvx squared plus p1y plus tvy squared plus p1z plus tvz squared is equal to r squared. And to find the points, all we have to do is to solve this equation for t. If we expand that equation, we get this, which we can rearrange by collecting terms as follows. And we can then convert this into vector notation, which makes it a bit easier to understand, which we can then rearrange to give where the dot represents the vector dot product. And we can further rearrange this into the form, and we can immediately see that this is of the form which is a simple quadratic, where, and we know how to solve this quite easily using. So that's it. We can test whether any given ray that we have cast into the scene intersects with the sphere using. If it does intersect, then we can solve for t and use that to compute the location of the intersection, which we can then go on to use for other things. That is really all of the theory that we need for this episode. So let's move on to having a look at how we can implement this in C++ code to create a very simple image of a sphere. Okay, so that's really, as I just said, the theory that we need, and we're going to move on to having a look at the code. Now, the first thing that I want to do is to create a class to handle spheres, but because I know that we're going to be going on to create other types of object, not just spheres ultimately, what I'm going to do is actually create a base class from which all of our object classes can then inherit. Now, the reason to do that is that there are certain things that are going to be common to all of the shapes or objects, the types of object that we're going to be using. So it makes sense to put all of that code into a base class. The other reason to do it this way is that by creating a base class, it becomes possible to use a single array or a single vector, STD vector, to store all of the objects in our scene regardless of their specific type. And we're going to look at that when we come to that, face that problem when we introduce another object in a later episode. But just so that you know, there is a good reason why we're doing it this way. It does initially seem like we're creating more work for ourselves, more code than we really need, but it does actually have a useful purpose, which we will see later. Anyway, let's jump into the code, and let's first of all have a look at how we create the base class. Okay, right. So to start with, I'm in the folder with the code. This is the code from the previous episode. If you've either acquired this from the GitHub repository where the code is now available, link in the description below, of course, or if you've been following the series, there should be the code that you've entered already. So this is, as I say, the code that we ended up with at the end of the previous episode. Now, the first thing I'm going to do is go into the QB raytrace folder. So if you remember, this is the directory where we're putting all of the code that actually does the ray tracing. And in here we have camera and classes for the camera, QB image, ray, and scene that we've defined already. And we also have the QB linear algebra library that we cloned from my GitHub repository in the previous episode. So the first thing we're going to do is we're going to create a new file which we're going to call objectbase.h. objectbase.hpp, in fact. Okay, so I'm in my text editor. I've created a new file. This is that's not right, is it? This is objectbase. Oops, if I could type, there we go. Objectbase.hpp, like so. So first thing we're going to do, as always, include guards object base h hash define object base h and hash endif. I've covered the purpose of include guards before. I'm not going to go over it again. We need to hash include some things. We obviously need to bring in from our linear algebra library, so qb linalg slash qb vector.h, because we're going to be using that. And we also need to hash include ray .hpp that we defined last week. And as before, we're going to keep putting everything into the qbrt namespace, so we define that. Now, we're going to create our class called objectBase, and as I said just now, the purpose of this is to be a base class from which all of our individual object classes can inherit, and it will contain all of the functionality that's therefore common to both of those. So First of all, public. So in our public section, we're going to have constructors and destructors. Okay, so constructor and destructor. Okay, so our constructor, very simple like that, default constructor. We don't worry in the base class about specific constructors. And now we come to our destructor, which we have to declare as virtual. Okay, and we declare it as virtual because it's intended to be overridden. So every class that inherits from this class will have to implement its own version of the destructor. Okay, and what else do we need? We're going to need, okay, we need a function. Okay, come on, function to test for intersections. Okay, function to test for intersections. This is virtual bool test intersections. So we're declaring this virtual again because every class that inherits and this one will have to implement its own version, and it returns a boolean of whether we had an intersection or not. It accepts as input a const ray reference cast ray. So that's a reference to the ray that's been cast into the scene that we want to use. You know, that's the ray we're going to test for intersections with. We then have QB vector double, like so, reference int point. So we're going to use that so that we can return the intersection point. We then have QB vector double reference local normal, which we can use to return the local normal. And finally, QB vector double reference local color, which we can use obviously to return the local color. Apologies for the line wrapping there, but I think you should be able to see what I've done. And we need one last thing. This is an interesting one which we're not going to need to use now, but it will be useful later. We're going to have a function to test whether test whether two floating point numbers are close to being equal. Okay, it's of course it's going to return a boolean. It's not virtual. This isn't designed to be overridden. Close enough. Const double, const double f1 and const double f2, like so. Okay, and we're also going to need some public member variables. In fact, actually, to be honest, just one, which is going to store the base color of the object. QB vector double m base color. And note that I'm sticking with COLOR spelling of color in all of the actual code. That's really to save confusion. I've had trouble with that before. Anyway, go ahead and save that. So that is object-based.hpp. Really just defines a few functions that we have to overload and a few other bits and pieces. So let's move on. Let's have a look at object-based.cpp. Okay, so this is object-based.cpp, and here we're actually going to define the stuff that we need. So first of all, we need to hash include, obviously, object-based.hpp, that makes sense, and we're also going to hash include math.h. Okay, we're going to define a constant called epsilon as being 1 times 10 to the minus 21f. Okay, we'll come back to that in a moment, and of course we need to define our default constructor, okay, which is qbrt : object base : object base. And we don't need any code in there, and we have a destructor as well. This is intended to be overridden, so we don't need to put anything here. Object base : tilde object base, like so, and again we don't put any code in that. And we have the function to test for intersections, which returns a boolean, bool qbrt : object base : test intersection, const ray reference cast ray, qb vector double reference point, qb vector double reference local normal, and qb vector double reference local color. Okay, color. Let's get that right. Otherwise, things are not going to work. In here, all we're going to do, return false, okay? Because that function is intended to be overridden by the inheriting class, though we don't really need to do anything. And the only other one here now is function to test whether two floating point numbers are close to being equal. Now, as I said, we're not going to actually use this function yet. It's going to come in useful in later episodes. So what I'm going to do, if you bear with me, is so those need to be const double f1, const double f2. It's really very simple. Simply going to return whether the floating point absolute value of f1 minus f2 is less than epsilon that we defined at the beginning. Okay, that's it. Really very simple, and like I say, we're going to talk more about why we need that later on in a future episode when we actually come to really do something with it. Okay, so that is everything we need for object-based.hpp and object-based.cpp. As you can see, it's really pretty simple, but it becomes incredibly powerful to use a base class like this, as you will see when we come on to start introducing different shapes and different object types in future episodes. Okay, so what I want to move on now, let's have a look at actually creating the class to allow us to create and define a sphere. Okay, so this is my new file, which is objectsphere.hpp. Okay, if we save that, and of course we need to do include guards as before, hash if n def object sphere h hash define object sphere h hash n def. Okay, and we need to include our base class object-based.hpp. Okay, so putting everything into the namespace as we've been doing, called qbrt, like so. Come on. Right, and we're going to define our class, which is object sphere, like so, but this is going to inherit from public object base, okay? And that's all we need to do. It's actually pretty straightforward. This means we create a class here called object sphere that is inheriting from object base, okay? Pretty straightforward. And now let's have a look at the public function. So we have, first of all, the default constructor. Now, actually, I want to comment that out a bit more. So we're going to define the default, the default constructor, and I just want to say note that this will define a unit sphere at the origin. Okay. Object sphere. Okay. Default constructor, no input parameters. We need to override the destructor. So we do virtual, that's the definition of the destructor, and override, like so. Okay, and we need to override the function to test for intersections. Okay, so for this we have virtual bool test intersection, and we know that it's const qbrt : ray reference cast ray, and then qb vector double reference intersection point, and qb vector double local normal, and qb vector double reference local color. Okay, pretty straightforward. And we can then have a section here for any private member variables or functions that we may need. At the moment, we don't need any of those, so we can just save that. So that is everything we need for objectsphere.hpp. Let's have a look at the equivalent objectsphere.cpp file. This is objectsphere.cpp. Of course, we need to hash include objectsphere.hpp, like so. And I'm also going to hash include cmath, I put there, that's okay. And then we define our default constructor, okay, which is qbrt colon colon object sphere colon colon object sphere. Okay, we don't need any code in there really at the moment, and we have, of course, the destructor qbrt colon colon object sphere colon colon tilde object sphere, like so. And again, we don't really need any code in there at the moment. So the one place where we do need, of course, code is function to test for intersections, and this is going to implement the maths that we were looking at just now at the beginning. So bool qbrt colon colon object sphere colon colon test intersection. Okay, and we have const qbrt colon colon ray reference cast ray qb vector double reference intersection point qb vector double reference local normal and qb vector double reference local color. Okay, so now the first thing that we need to do is, we saw before that the situation of detecting whether we have an intersection between a line and a sphere simply boils down to actually solving a quadratic equation, which is pretty straightforward to do. So the first thing that we need to do in our code is to define the values of a, b and c that go into the B standard formula for solving quadratic equations. Okay, so let's look at that. So we're going to compute the values of a, b and c. Okay, this is pretty straightforward. So the first thing we need is to know the direction vector for our line. So we're going to define a new QB vector type double, which we're going to call v hat. And we get that from cast ray, which is the ray that's been cast into the scene. And we want cast ray dot m underscore lab, like that. Okay, so if you remember back to when we created the ray class in the previous episode, it stores the start point and the end point of the ray, and then it also stores the m underscore lab vector, which defines the direction. And then we're going to normalize that, so just do v hat dot normalize, okay, to normalize in place. Okay, now this is an interesting point here. We have to note that a is equal to the squared magnitude of the direction of the cast ray, okay? As this will be a unit vector, we can conclude that the value of a will always be 1. Okay, that's an important point, because it means that we can actually just ignore the value of a. We know that a is always going to be equal to 1.0, right? So we don't need that code, we just put it there as a comment. We do, however, need to calculate the value of b. So we have double b, that is simply equal to 2.0 multiplied by qb vector double colon colon dot for the vector dot product cast ray dot m underscore 0.1, that's the start point of our ray, comma v hat, okay, just that. And we need to calculate c. I'm just going to put some lines in there so we can see more clearly what we're doing. Now c we calculate in a similar way. Now double c is equal to qb vector double colon colon dot for the vector dot product of cast ray dot m 0.1. As I said before, that is the start point of our cast ray. Oops, I didn't realise that should be cast ray. There we go. And cast ray dot m 0.1. So we're taking the dot product of the start point of the cast ray with itself, which is the same as taking its squared magnitude, minus 1.0. Okay. Now we need to test whether we actually have an intersection. Okay, and we know that we can do that using, so we just define double int test, and we know we can do that using simply b squared minus 4 times a times c, but of course we know that a is equal to 1, so we don't need to bother with it. Okay, now, so all we're going to do to start with, I want to keep this as simple as possible, so we're simply going to put in an if statement. So if int test, okay, is greater than 0.0, so in that case we know that we have an intersection, Okay, so we have an intersection, so we're going to return true, else return false. Okay, so keeping things very, very simple at the beginning, all this function is going to do is take as input the ray that we've cast into the scene, and it's simply going to test whether that ray intersects with our sphere. Our sphere is defined as being a sphere of unit radius centered on the origin. We can't change that, so that's all pretty straightforward. The maths is very simple. We just test whether b squared minus 4ac is greater than 0. If it is, we have an intersection. If it isn't, we don't. We return true if we have an intersection, otherwise we return false. So that's really pretty straightforward. What we need to do now is take a look at how we can actually modify the code that we've already written to use this to actually create an image of a sphere. So let's have a look at that now. One thing that I realized I didn't do quite as well as I could have done before is in the camera class. So I've gone ahead and opened the camera.hpp file that we were working on in the previous episode, and want to make a small change here to the definition of the generate ray function. We want it to return a boolean, and instead of passing ray, we are going to have it accept as input a reference to a ray object, which we call camera ray. So that just makes things a bit more efficient. So let's save that, and now let's go to camera.cpp and see what changes we have to make there. Okay, and we look down at the end of this where we defined, here we go, this is the generate ray function that we defined before. So we just have to modify this now so that it returns a boolean, like so. And we add here that we accept qbrt : ray reference camera ray. Okay. Now we leave everything here the same, and use this point along with the camera position to compute the ray. So what we're going to do is simply return true, return, no, that's not right. So we simply return true like so, but for that, we're going to do camera ray dot m point 1 is equal to m camera position. Okay. Camera ray dot m point 2 is equal to screen world coordinate that we've defined here. Okay. So all we're doing is modifying the property. So we assume that ray has been defined previously before this function was called, and we're going to modify its parameters in this way. And we also need to modify camera ray dot m underscore lab is equal to screen world coordinate minus m camera position, just like that. Okay, let's save that. Okay, that's everything that we need to change in the camera class. Okay, so in ray.hpp, this doesn't actually have a comment there to say what it is. This is ray.hpp. Okay, what I've done here is simply go ahead and define a default constructor. Okay, we didn't have that before, but I want to have a default constructor, so we simply put that in like so. Okay, and let's look at ray.cpp. Okay, put a comment there. This is ray.cpp. Okay, and let's add the definition for the default constructor there, which isn't really going to do very much. It's simply going to create a default ray. So qbrt : ray : no inputs because it's the default constructor, and we have m underscore point 1, and we're just going to set these up with some default values. It's qb vector double initialized with std vector double 0.0, 0.0, and 0.0, like so. And m.2 is qb vector double std vector double, and we can, just for the sake of interest, put something different, and then we define mlab is equal to m.2 minus m.1. Okay, and save that. Okay, that's everything that I've changed in the ray class since the previous episode. Okay, so that's in scene.hpp. What we need to do is just hash include the other things that we just created. So we've created camera.hpp, actually in the previous episode, but we're going to start using it now. And we're also going to bring in object sphere.hpp like so. Okay. And yes, here we go. Just down here in private members, we're going to define a couple of things for our scene. So we have the camera that we will use. Okay, so we create qbrt : camera m camera, And we're also going to want to define a unit sphere on the origin for testing. Okay, qbrt : object sphere m test sphere, just like so, and save that. So that is scene.hpp. Now let's look at the modifications we're going to make to scene.cpp to actually make it do something. So here we are. This is scene.cpp, which at the moment is incredibly simple. This is simply the code that we wrote in the previous episode that made the color variations, and we're actually just going to go ahead and delete that code, okay, leaving us like that. Right, and now what we need to do, in our default constructor for our scene, we need to put some code. We need to configure the camera. Okay, so we are going to do mCamera.set position and QB vector double, okay, std vector double. So I'm going to put the camera at 0 on the x-axis, minus 10 units on the y-axis, and 0 on the z-axis. Okay, just like so, like that. And we're going to do mCamera.set lookat. Okay, QB vector double std vector double, like that. And we're going to look at the origin 0, 0, 0, like so. mCamera.set up. Now, to some extent, these are actually defined by the default camera, but I do like just to be quite explicit about things. So we have std vector double, and this is our up vector, which is of course 1 unit in the z-axis. Yeah, it's not necessary to tab things out like that, but I just like to do it so things line up properly. We're going to set mCamera.set horizontal size to 0.25, okay, and m_camera set aspect to the aspect ratio of our screen, which is 1280 by 720, which has an equivalent aspect ratio of 16 by 9, okay, and then we need to remember mCamera.update camera geometry. Bad things happen if you forget to do that. Okay. So that is now the constructor of our scene. When we create an instance of the scene class, that will then configure the camera using those properties. And now we're going to look at the actual function to do the rendering. This is where things really start to get a little bit interesting. And this is really now implementing ray tracing, which is quite exciting. So far we've really just been doing all of the background and everything that we need. So finally we're actually going to look at doing a very basic initially implementation of the actual ray tracing algorithm. Okay. So what we do first is we simply loop over each pixel in our image. And as we've seen in the previous episodes, we know that we are going to cast a ray out through each pixel in our screen. So each pixel in our image corresponds to effectively one of the pixels in the virtual screen, as we saw in the simple introduction. And we're going to therefore cast a ray out, one ray corresponding to every pixel on the screen, and then we use that to calculate what the colour of that pixel should be, and that of course is how we generate our image. Okay, so loop over every pixel of our image. Let's first of all define some things that we need. We need qbrt : ray camera ray. That's the ray that we're going to generate for each pixel. QB vector double intersection point, and let's just tab things out, keep things nice. QB vector double local normal. Okay, it's 3. So this is simply going to create these instances of the QB vector class, QB vector, and that is local color, also 3. So simply create instances of the QB vector class with 3 elements. Now, as we discussed when we looked at the camera class in the previous episode, it's designed to accept inputs for the generate ray function, which are normalized screen coordinates that vary between -1 and 1. And of course, we're going to loop over the coordinates about the pixels of our image, which run from 0 to 1279 in the x-axis and 0 to 719 in the y-axis. So what we need to do is convert those pixel coordinates into normalized coordinates between -1 and 1 that we can then pass to the camera generate ray function. And rather than having to do all of those calculations for every single pixel, we pull out of the loops as much as we can. So we pre-calculate multiplication factors that we can use to do as much of that scaling as possible. Okay, so let's look at that now. So we define double x fact for x scaling factor is equal to 1.0 divided by static cast to double. So static cast double of x size. Okay, now we have x size is here, okay, from before, and we static cast that to a double divided by 2.0. Okay, so that's going to give us a value that varies between 0 up to 2. And we do the same thing for y fact. Y factor by static cast double y size divided by 2.0. Okay. And we're also going to define a minimum distance, which starts out as 1e6, and max dist, which is equal to 0.0. We'll see what we need those for in a moment. And then we do our loops for int x equals 0, x less than x size plus x, like so. I'm just going to put some lines in there. Right, so more in the center, and of course we have our loop for y. 0 y less than y size plus y. Okay. Right, like so. So the first thing that we need to do in our loop is we need to normalize the x and y coordinates. Okay, we can do that quite easily. So we create double norm x is equal to static cast to double of x multiplied by x fact that we just defined minus 1.0. Okay, and the same for norm y. So we see these initial values up here, these will vary between 0 to 2, and we then subtract 1 from the result. So in fact, when we multiply x by x fact, we get a value that varies between 0 and 2, and then we subtract 1, which then gives us a value that varies between minus 1 and plus 1. Okay. Static cast double y multiplied by y fact minus 1.0. Okay, pretty straightforward. And now we're going to generate the ray for this pixel. Okay, so camera dot generate ray norm x norm y and the camera ray instance that we just defined. So we defined camera ray here, okay, and then we're passing it to there. So every time we call the generate ray function with norm x, norm y, it is going to modify the properties of camera ray that we've already defined. And now we're going to test if we have a valid intersection. So we simply do bool valid int is equal to m underscore test sphere that we defined dot test intersection, and we pass camera ray int point local normal and local color that we've just defined up there. Okay, that's pretty straightforward. And now we're actually going to do something that's going to modify our image, and we're going to do this very, very simply to create a very simple image first. Okay, so if we have a valid intersection, change pixel color to red, really basic. So we simply do if valid int, then output image dot set pixel x y, and we want to set it to red, which is 255.0, 0.0, 0.0, just like that. Okay, else output image set pixel x y to 0.0, so just for black. Okay, so if we have a valid intersection, we set the pixel to red. If we don't have a valid intersection, we set the pixel to black. And that is actually everything now that we need as for our basic code. So that's the modifications to that is scene.cpp. We need to make, before we can actually run this and do something, we do need to make some minor changes to the capp class. So let's have a look at that. Okay, alright, so in capp.cpp, what we did before when we created this initially, we put in the onRender, we have all of this code here that rendered the image every time it came through. Now, because our ray tracing takes a little bit of computing time, it's not that quick. What we're going to do is simply comment all of this out. Okay, we're not going to worry about that in the onRender method. What we're going to do instead is go back up to onInit. Okay, so we initialize our image here, and then we've got this code that we used before to test the camera class and things, so that's from the last episode. What we're going to do is just delete that. Okay, so we initialize our image instance, and now we're going to set the background color to white. Right, so we do that with SDL set render draw color p renderer 255 255 255 255 like so, and SDL render clear p renderer. Okay, we're then going to render the scene. It's easy. Underscore scene dot render to n image like so. Display the image. Underscore image dot display like so, and we of course simply need to make sure that we actually show the result, which is SDL render present p renderer. Okay, so essentially all we've done there is move the code from the render function, which is in the loop, into the init function, and the point of that is it will only run one time, and then the window continues to be displayed and we can see the result. Right, so that's basically all of the code that we need to change. We should be able to run that now. So let's go to the terminal and see if we can compile that, hopefully without too many errors. Okay, so let's check I'm in the right place. I need to go back. So we can see in the QB Raytrace folder, we see we've created object-base.cpp and HPP, object-sphere.cpp and HPP, and of course we altered the various bits of other code. So if we go into here, if we run make, that should now run through and compile all of the code that we've changed, and of course, yes, that is an obvious spelling mistake in object-sphere .hpp line 21, so let's look at that. So object-sphere here we are, yes, virtual, of course. Right, I'll save that, go back to the terminal. Okay, here and run make again. Now, this is compiling everything because I'd run make clean before we started, so it's going to run through. Okay. What's wrong with that? No. Member function declared in object base. Okay, interesting. Okay, yes, there is the mistake. So in object-base.hpp, I put that as test intersections. Okay, so it's actually, of course, just test intersection. Right, so let's delete that erroneous S. Let's save that. Go back to the terminal. Run make. No. Now what's wrong? Undefined reference. Test intersections. Indeed. Okay, so let's just run make clean, tidy that up, and run make again. Okay, and that all compiled. So if we run our code now, so do /qbray, we initially get a blank window, and after hopefully not too long a time, it stresses my computer out a bit when I'm running the screen recorder at the same time. There we go, we get an image of a red circle, which may not seem tremendously exciting, but I think it actually is pretty cool because we've generated that using ray tracing. We've mathematically defined a unit sphere centered at the origin, and we've created our virtual camera, and we've put everything together, and we have created what is essentially our first ray traced image. Now obviously ray tracing usually creates nice shiny reflective objects with shading and lighting and all of that sort of thing going on. Right now we don't have any of that. So we can't really tell for sure that that is a sphere and not just a 2D circle created in a tremendously inefficient way. In order to illustrate that it is a sphere, I'm going to add some very basic shading. So what we're going to do is shade the colour of this based on distance from the camera. I don't want to talk about introducing lights and things in this episode, as I think that would be far too much. So we're going to look at shading this sphere based on its distance of every point from the camera. And that also allows us to test that our intersection points are indeed in the right place. So let's look at how we do that now. Okay, so let's just close that. Now, one thing to note is that that did take quite a long time to render, and there's actually something that we can do just to speed that up before we look at actually doing any shading. Okay, so this is the make file that we created before and that we used to do our build. And the one thing is we have here, we define flags here that we are going to pass to the compiler when we compile our code. Okay, that's pretty straightforward, but there is something that we can do that makes everything a lot quicker. Just want to make sure I get this right, and yeah, there. Okay, yes. So here we go. We're not going to pass only, instead of only passing the C++17 flag, we're going to also pass -O and fast. Okay, if we save that, what that does is change how the compiler approaches optimizing our code, and it actually makes an enormous difference. So I just want to show that. Let's just go back to our terminal window. Let's run make clean, run make again. And now you can see it's put the -O fast flag on everything. It'll take slightly longer to run the compilation, to do the compiling, but the difference it actually makes to the speed of execution of the final code is really quite tremendous. It's really worth doing. Okay, so now if we run it, to run /tbray, it brings up the blank window, and there you see, almost quicker than I could move the window from one of my monitors to the other, the image has come up. Now I timed this before without using my screen recorder, and it took something like 6 seconds to create this image without the -O fast flag, and with it is a lot less than 1 second. So it really makes a big difference. It's worth doing. Anyway, okay, let's stop looking at that. So what we want to do now is to look at how we can actually add some shading to that. Okay, so to do that, we come back to objectsphere.cpp. Okay, so we're going to need to add a little bit more code here to the test intersection function that we've created before. So we've already defined, we test whether we actually have an intersection or not, and that's what we use to create the very basic image. Now, we want to do something a little bit more complicated. If we have an intersection, we want to try to calculate where the intersection occurred. Okay, so let's just get rid of that return statement for now. And so within this if block statement here, we're going to define a variable called num_sqrt, which is the square root of the numerator of our quadratic equation solution is equal to square root f floating point square root of int test. Okay, like that. So int test we've already defined is b squared minus 4ac, so we take the square root of that, which I've just called num square root for numerator square root, okay, and then we can calculate the values of t1 and t2. It's a quadratic, so of course we get two answers, which are given by -b plus the square root of b squared minus 4ac divided by 2a, and of course we know the value of a is 1, and t2 is going to be -b minus num square root divided by 2.0. Okay, now what we're going to do, if either t1 or t2 are negative, then at least part of the object is behind the camera, and so we will ignore it. Okay, that's not strictly necessary for the code we're writing today, but will become very useful later on. So if t1 is less than 0 or t2 less than 0, okay, then we return false because we're not going to do anything with this object, right? Else. Right, now in this else block, this is where we're actually going to do the work that's going to calculate our shading. So what we need to do really is to calculate the point of intersection. Okay, so when we define this function, it has this input here, a reference to int point into which we can put the point of intersection. So that's what we're going to do. So we need to determine which point of intersection was closest to to the camera. So of course we get 2 points of intersection. It's a sphere casting a ray through it, so it's going to intersect the sphere at 2 places. It's possible there might only be one if it's just literally grazing. Okay, that of course can happen, but in that case int test I believe would be exactly equal to 0. So we're not going to detect that situation, and that works well enough. So we need to determine which one is closest to the camera, and we can do that simply if t1 is less than t2. Okay, that means that t1 is closer to the camera, so that's the point that we want to use. We don't worry about the back face of the object. We're not interested in that because we can't see it anyway. So the intersection point is cast ray dot m.1 plus v hat times t1. So as I said in the introduction at the beginning, we can define any point along a line simply by adjusting the scalar value t. So we have our start point, we have a direction, and we have the scalar t. Okay, so you can see how that works. So in this case, t1 is closest to the camera, so we use t1 to get the point of intersection. Okay, else. And here int point is going to be equal to cast ray dot m.1 plus v hat multiplied by t2. Okay, and that's it. That will now, instead of just returning true or false, it still does that, whether we have an intersection or not, it will now update the value of int point to be a vector that indicates where that point of intersection was. So let's save that. So we now need to go back to scene.cpp. Okay, so back in scene.cpp, we're going to modify this now to make use of that additional information. So we already defined int point here, so what's going to change now is that's going to get updated with the actual location of the intersection each time we call it. So we can do something more interesting. If in this point here, if we have a valid intersection, okay, if that's returned true, what we're going to do is compute the distance between the camera and the point of intersection. Okay, so we do double dist is equal to intersection point minus camera ray dot m.1, which is of course the start point of the ray dot norm. Okay, so we're taking the norm of the difference between these two vectors, which is of course a scalar quantity that will be equal to the distance. Now, we defined these two variables up here. We defined min dist and we defined max dist. Okay, what I want to do is we loop through it. I want to record the minimum and maximum distances that we get from the camera. This is really just for debug. We can use it to see that things do indeed make sense. So if dist is greater than max dist, then we do max dist equal to dist. Okay, and similarly, if dist less than min dist equals dist. Okay, that's pretty straightforward. And what we're going to do to actually create a more interesting image, we're not just going to pass 255.0 for the red channel. What we're going to do is 255.0 minus dist minus 9. Okay, now these are not random values, they all have a purpose, we'll see in a moment. 94605, like that, multiplied by 255.0. Okay, and save that. Right. Okay, now let's run that first and I'll come back and we'll talk about those things. And, oh yeah, one more thing to do. Where are we? Yes, so just here, just before we return true, I want to do std cout, and I'll just want to print these out to the terminal. So minimum distance was min dist, okay, just like that, std end l, and std cout maximum distance, max dist, okay, just like that, std end l, and save. Okay, let's go to our terminal, and hopefully that will compile without any problems. Okay, so if we run make, the make file should only compile the files that are changed. So we run /qbray. Okay, those values don't make any sense, and everything is just blank. Oh, why? What have I done wrong? Okay, so that's actually a fairly simple mistake. So in this function here, in this case where we have the valid intersection, I forgot to replace the return true. I did delete it, and then I didn't replace it. Okay, so we have to return true in the event that we have a successful intersection. Okay. So back to my terminal, let's just run make and /qbray. There we go, and that happens so quickly, I have to switch that over. And now we see we have a much more exciting image. We now have a properly shaded image of a red sphere. The shading has been achieved by shading according to distance from the camera. And we can see from the values that we printed out to the terminal, we have a minimum distance of 9 units and a maximum distance of 9.94605 units. Now, if you think about what's happening, we positioned the camera at -10 units along the y-axis, and we put the sphere is at the origin, obviously. Now it's a unit sphere, it has a radius of 1, and that means that the closest point on the sphere to the camera is going to be 9 units away, 10 minus 1, okay, so it gives us 9, and the sphere has a radius of 1, so the center point around here, the furthest away points that we can see are going to be just a little bit less than 1 unit away from the minimum distance, so we get 9.94605. And of course that's where the values in the code that we were looking at just now came from. I didn't just derive those randomly. So the interesting question really is, why do we need to do that? And if I just go back and look at the code again, in scene.cpp, so what we did is we did initially dist -9, so that's going to make the values of the distance, obviously, are going to be 9. Okay, so the closest value to the pixel to the camera is 9 units. So dist -9 means the minimum value that we get here is going to be 0. And then we divide by 9.94605 minus 1, which of course gives 0.94605. Okay, so that's now going to give us a value that varies between 0 and 1, which we then multiply by 255, that gives a value that varies between 0 and 255, and then we want to invert it, so the minimum distance is the brightest red, so we do 255 minus that, okay? Now, the interesting thing here, because the values vary between 9 and 9.94605. They don't vary between 0 and 10 or something like that. And this is really a question of dynamic range. And this is the whole reason why I created the image class in the way I did, using double precision floating points to store the colors. And we're going to see a lot more about this later, particularly when we come to talk about lighting and shading and things, because what we're going to do ultimately is modify the image class so that it automatically optimizes the dynamic range of the image based on the values of the color. So at the moment, just for this example, we've done it here in the code as a hard-coded thing, but ultimately we will in a future episode modify the image class to take care of that for us automatically based on the values that are actually in our image. Okay, so that's really everything that I wanted to talk about today. We have actually now created some ray tracing, which I think is really pretty exciting compared to what we had before, and we can now go on to do all sorts of more interesting things with that. So we looked at the way that we've structured the code. We created a base class for all of our objects, which contains everything that is common to every object, and then we're going to create new classes that inherit from that will define all of the different objects. So today we focused just on a simple sphere, and we looked at how we can then create a sphere shape using the render function from the scene class, and how we can modify that to make that work. And then we shaded the sphere based on distance from the camera, which allowed us to discuss a little bit about dynamic range as well. So that's really enough for today. I think this video is already long enough. So in the next episode, I'm probably going to go on to talk about lighting. I have been having some thoughts about exactly what the best sequence of things are for these videos. I think lighting is probably the logical one to come next. So we're going to look at basic principles of lighting and ray tracing in the next episode. Anyway, as I said, that's really everything I wanted to cover today. So I really hope you've enjoyed this video. It's been a great deal of pleasure making it. If you have enjoyed it, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. The next video will be even more exciting when we start to talk about lighting, so if you subscribe, then you're not going to miss it. Thank you very much. Anyway, listen, it's been a pleasure. Thank you very much for watching. I really hope you've enjoyed it, and I really look forward to seeing you in the next video. Bye.